una prova per domani. Io arriverò qui con le slide. Questa è una carina. Sì, ma infatti perché io questo non lo vedo. Ready?
Possiamo provare a farlo dopo che non sono niente, ti spiace? Che letta che inizia da
Sì,
20
no, ma
minuti.
prego, facciamo fare a lei, intanto io guardo se questo
va bene,
funziona o
va bene.
meno. Che infatti non funziona neanche questo.
Vai, stacca questa.
Cioè fate fare pure tutto quello che volete fare con lei, ma in realtà non funziona neanche questo. Ne avete un
Possiamo
altro?
trovarne uno allora. Ma non è forse più facile che ce la mandi?
È enorme.
Quanto è grande?
Ma uno è 20 mega. Non ne avete un altro?
Possiamo vedere ancora un altro. No, ne abbiamo solamente un paio, però se forse inizia con un paio che non funziona, ma che se me lo mandi, vedi come funziona io.
Va bene, questo è uno e l'altro è qua.
Ma tu hai Dropbox per caso?
No,
Google Drive?
no. No, cerchiamo di farlo con una chiavetta che...
No, la cosa più semplice è la chiavetta, solo bisogna trovare qualcosa che lo collega.
Let's try just to see.
Allora, quello che posso fare, però allora adesso dentro il break adesso devo un'ora. Posso andare con gli altri colleghi che si sono altri.
Ok, perché questo non so come mai non è...
So you point them at me, and I obviously now I will pass through. Yeah, exactly.
Okay, that's great. So
That's
when I
great.
get done with that, I'll just give it to
Yeah,
you.
exactly.
Se ci spostiamo giusto un attimo, devo
Sì,
capire gli spazi.
tanto non è che occupiamo...
Là, casomai così va un attimo sopra nel frattempo. Antonio, non hai bisogno di questi, no? Me li prendo per un attimo.
Yeah, no water. We're here.
Because nice. Huh?
Yeah, it's working.
It's working. Yeah.
You cannot see.
It will not see.
We will be displayed there afterwards.
Okay.
He is the room in charge of that. Yes, it works. Okay. Great.
Great.
Okay, let me.
We are, and let me just see the pointer. Let's see if I can see the pointer.
Yeah, you
I can. Okay.
Yeah, yours.
No, but I don't want to look up. I want to keep looking at the
Okay,
others.
okay.
Otherwise
This is
it's
the
a bit-
challenge.
yeah.
Otherwise, I have to do this.
Also,
It's
the
not good.
neck is not
Yeah.
good.
No, and I give my back to the audience.
I see.
This because then I can do this.
Give it a try. Okay. Put it off. It's working.
try and
All right, good afternoon, and thank you for coming to our keynote lecture. I'm really delighted to have the honor of introducing to you Dr. Alexandra Schmidt. Alex received her bachelor's and master's degrees from Federal University of Rio de Janeiro in Brazil. She then earned her PhD at Sheffield under the supervision of Tony O'Hagan, and in a JRSSB paper from her dissertation introduced deep GPs. She was the first postdoc of Alan Gelfand, and then she became assistant professor at our alma mater in Brazil. She's been a professor at McGill University for the past 8 years. Alex has contributed immensely to our society in many different roles, ranging from chairing the program council, to chairing the World Meeting Local Organizing Committee, to serving on the board of the directors, to serving as our president, and in her current role as co-editor of Bayesian Analysis. She's made a large number of really notable contributions to the modeling of spatial multivariate processes and the use of covariant information and the covariant structure of spatial processes. Now, along with her many important scientific contributions, she's a wonderful mentor and colleague. You'll always find her building up others. My interactions with Alex always improve my days, and I'm sure many of you would say the same thing. So without any further ado, I'll give you Dr. Alex Schmidt.
Thank you, Amy. Don't make me cry. I'm very emotive. I can laugh and cry very easily. Good afternoon, everyone. It's a huge, immense pleasure to be here this afternoon. I would like to start by thanking the scientific committee for the invitation. As I said, it's a great honor to be here, and also to thank the organizing committee. I know where you are. I was there in 2022, so thank you for putting together this amazing meeting. Grazie mille. Yes, please. So today I'm going to talk about moving beyond normality in multivariate spatial and spatiotemporal processes. I added multivariate into the title of the talk because actually I plan, if everything goes well, I plan to focus my talk on very recent work that I am doing with Paritosh Kumar Roy, a PhD student at McGill University, and Thais Fonseca, associate professor at the Federal University of Rio de Janeiro, where I'm originally from, where Danny Gammerman and Elio Megon started a Bayesian group many years ago. So basically, usually I'm interested at modeling data that sometimes I have only information, I have only spatial information across a region. Here's the map of the UK with some monitoring sites of ozone. Sometimes at each site I have also the time series observed at each of the sites. But usually these sites are planned to monitor more than one pollutant. So on the bottom line, we also have measurements of PM10. So on the top, we have ozone. On the bottom, we have PM10. And sometimes, some days, we have their mean levels of ozone and PM10. We have some spikes on the time series. Or if you look at the map, there are some areas with quite red values, indicating high values that maybe they are following on the tail of the distribution. So the goal of this talk, if everything goes well, is to reach the end by proposing a spatial-temporal model for heavy-tailed processes. But to put everyone on the same page, and of course, when you are on the talk, the mouse doesn't work as when you trained it. But anyway, let's define what a Gaussian process is. So if you have a function, you have a random function, we say that it is a Gaussian process with mean function m and covariance function c. If for any set of locations in your domain region D, you have the joint distribution following a multivariate normal distribution with mean m and covariance function c. So all you need is as if it's easy, but all you need are these two functions, the mean function and the covariance function. And once you specify them, the process is fully specified. It's kind of easy in terms of interpretation of associations between the outcome of interest and the covariates. And spatial interpolation, because this is what we want in the end. I should have mentioned that in my previous slide. What we really want in the end is like to come up with a surface across the UK that will provide the estimates of PM10 ozone across the region. So spatial interpolation follows using properties of the multivariate normal distribution. Given the parameters, you have a conditional multivariate normal distribution, it's easy to interpolate from. But as we know, and we have been discussing, we started discussing yesterday, the computation of the inverse and the determinant of the n-dimensional covariance matrix that we have can be quite expensive. So the inference becomes expensive when n is reasonably large. In the analysis of most spatial temporal processes, we usually are faced with observations that present heavy-tailed or they are skewed. And usually a transformation of the response variable follows a Gaussian process. This is the assumption that we make. Usually we take the log or the square root, and then we assume that the observations follow a Gaussian process. And then we make another assumption of stationarity and isotropy, that the process is homogeneous. This means that the distribution is unchanged when the region of the index set is translated and the process is invariant under rotations of the coordinate system about the region. But when you are thinking about environmental processes, ozone, for example, this might be a very strong assumption because you might have wind blowing in one direction and you expect that the observations across that particular direction are more highly correlated than observations made at other locations in different wind directions. So as Amy was saying, my PhD was about proposing a Bayesian version for the landmark paper by Paul Sampson and Peter Gurtop that was published in JASA 1992, where the idea was that they estimated a latent space that they called the D space, wherein isotropy held. And the way that they did the inference, they proposed the inference was a two-step approach such that the uncertainty was not clearly accounted for. My PhD thesis was about proposing a Bayesian version for this approach such that the mapping from the original geographical space into this latent space follows a Gaussian process a priori. Little did we know back then in 2000-2001 that we were working with deep Gaussian processes and we were introducing the idea of deep Gaussian processes. And very recently, in a JASA paper in 2021, Andrew Zemet-Manjian, together with his collaborators, took this approach to another level that now it avoids the folding, which was a problem of our original paper. Another way to handle non-stationarity is to assume a convolution approach such that you have a convolution of white noise. You can build your Gaussian process, and there has been quite a bit of proposals along these lines. I highlight the one by Patrak and Chevrish, where they propose a non-stationary Matern covariance structure. About 13 years ago, with Peter Gurtop and Tony O'Hagan, we extended the latent space idea by mapping it into a space that was greater than two-dimensional. So, for example, if you are observing ozone, sometimes altitude might be important, and then the latent space can be of a dimension greater than 2. And we came up with this idea of using covariate information to include in the covariance structure, but this is challenging because, as we know, the covariance function, the covariance has to be positive definite, so we cannot include covariate information in any way. Then there is the SPD approach by Finn Lindgren, Hoover Drew, and colleagues that is quite flexible and is able to accommodate non-stationarity. But as I said, all these assumptions, as far as I remember, well, most of them, they assume that you have transformed the data to attain normality. And in this 2015 paper in the Scandinavian Journal of Statistics, Wallin and Bolin, to motivate their proposal of a non-normal model, they look at the square root of the square root transformation and how it affects the mean and the variance of the original process. And clearly, the covariance structure depends on the mean. So when you transform the data and you fit a non-stationary model to that transformed data, you might wonder, is the non-stationarity because the process is really non-stationarity, or is it induced because of the transformation that you are using? So maybe we should start thinking about modeling the data on their original scale. So this is the motivation behind my work. And there has been many different proposals along these lines. One of the initial ones that I'm aware of is this paper by Victor de Oliveira and colleagues in JAS in 1997, where they proposed to estimate the Box-Cox transformation parameter together under a single framework. One of the issues with this approach is that if you want to discuss associations, it becomes a bit challenging because you are changing the scale of the outcome as the parameter of the Box-Cox transformation changes. But in terms of interpolation, it's an interesting approach. Then there is the red paper by Peter Digo and co-authors in the Royal Statistical Society in 1998 that proposed a conditional spatial model. So you transform the mean, and given a transformation of the mean, you have this linear combination and then a latent process. And recently, with a former master student, he was interested in looking at levels of arsenic across Bangladesh. And some of his data were censored, and we decided to explore a gamma distribution. Because I have always wondered, the gamma might be an interesting distribution to be used because it's strictly positive, it accommodates skewness, but it's not so easy to work with the gamma. And actually, we proposed different parameterizations of the rate and shape parameters. We got some interesting results. And actually, when we compared the proposed gamma models with the current skewed models in the literature, the gamma one seemed to perform better for this data set. But what class of skewed spatial models did we look at? We looked at these models that one way to induce skewness is to assume that your process is this linear combination, and you have now, instead of one process to accommodate the spatial structure in your data, you have this transformation of another independent Gaussian process. And there has been two proposals in the literature for this transformation. One is that he uses the absolute value of this Z1, and it was proposed by Zhang and El Sharawi in an Invermetrics paper in 2010. And the sigma 1 in this case is associated with the skewness parameter. Another possibility is to use a log normal distribution, is to say that the Z1 process follows a log normal. And this was proposed by Zarefad and others in 2018. And that previously, a PhD student that was supervised by Thais and myself at the Federal University of Rio also worked on this model, but when we were preparing the paper, we saw this one in Bayesian analysis, and then the work kind of stopped. But anyway, because we were yesterday talking about PhD students and how committed they are, but sometimes life comes in place. One extension that I have worked with another former PhD student, Patrícia Veloso, and a colleague in Rio, Kelly Gonçalves, is a spatiotemporal version of this paper. So basically what we did, we allowed the sigma 1 to change across locations, because as we had replicates across space, we were able to estimate a different sigma 1, a different skewness parameter at each location. But again, with the replicates, we were doing a reasonably good job. Recently, Paritosh and I studied approximating methods, because as you have, if with one Gaussian process is already challenging to make inference when you have a big number of locations, with two it becomes even more challenging. So Paritosh did this, he worked on proposing different approximations for this process, and this paper has just actually, is available online today, from today at JABS. But the talk is not going to focus on this. I want to actually focus on scale mixture models. As I said, there are many different proposals in the literature. I apologize if I'm missing your reference. But one of the possibilities is using SPDs driven by non-Gaussian noise. Zhang, Cotas, and Sansur have an interesting paper in Bayesian analysis that proposes a nearest neighbor mixture process for univariate spatial process that seems to scale well and accommodates skewness. A very recent paper by Dovi Bolin, Ru, and Rafael Cabral in JASA in 2023 proposes a normal inverse Gaussian mixture model that apparently also accommodates skewness. And here, as I said, from now on, I'm going to focus on scale mixture models and the models I'm going to discuss, they are able to accommodate heavy tails and symmetric distributions. A very brief literature review of scale mixture models to motivate the use of scale mixture models. Michael Stein in 2009, he discusses in this paper the presence of peaks in the temporal variance in the modeling of atmospheric pressure. And this is even after including altitude in the mean function. So it's likely that the observed pattern is possibly due to the passage of weather fronts over the region. Then in a very nice paper in 2006, Blanca, Palacios, and Steele proposed a non-Gaussian process for point reference data that accommodates fat tails by scale mixing a Gaussian process. And what is nice is that the Gaussian case, the Gaussian model, is a particular case. And actually, I had the pleasure to meet Blanca Palacios last week in Pamplona. It was really nice. And then Thais Fonseca, my collaborator, she did her PhD with Mark Steele in Warwick, and they published this paper in Biometrica in 2011, where they extended Palacios and Steele to the spatial temporal case. The point is that they are proposing, in this 2011 paper, they are proposing a model for continuous space and continuous time. Therefore, the covariance matrix becomes even more challenging because now we are talking about an n times t dimensional covariance matrix. So the computation, if you have too many points in time, too many points in space, the computation of this covariance matrix becomes really challenging. Renata Bueno, the former PhD student that I was telling you about that worked on that log Gaussian convolution between a Gaussian log Gaussian processes, also worked on an extension of Thais' paper with Mark, where we included, because you will see the model soon, we have this mixture component, and what we did in this paper in spatial statistics, we included covariate information. This was motivated by the work of this idea of including covariate information in the covariance structure, but we are still considering time as continuous here. Then last year, together with Thais and Viviana Lobo, who is another associate professor at the Federal University of Rio de Janeiro, we published this Series C paper, where now we are looking at the class of dynamic linear models, which I will talk about in a minute. And we allow, now instead of treating time as continuous, we are treating time as discrete. And we use the whole framework of dynamic linear models to include these scale mixing components such that we have a class of heavy-tailed dynamic linear models. So the rest of the talk now, and it seems I'm fine with time, I will focus on the recent proposal of thinking of a heavy-tailed purely spatial process and then a heavy-tailed multivariate spatial temporal process, okay? So this is joint work with Paritosh Roy, who is doing a PhD at McGill under my supervision, and also Thais Fonseca at the Federal University of Rio de Janeiro. So let's start with our proposal for the heavy-tailed multivariate spatial model. When I did my postdoc with Alan Gelfand, one of the projects that we worked with was on a proposal for multivariate spatial processes. So if you still remember the initial image that I showed you, we had on the left-hand side a map of two maps of the UK, one where the solid circles were colored by the level of ozone, then on the bottom by the colors were the level, the colors followed the levels of PM10, and this is quite typical in environmental problems. We have multiple observations at each location. And the challenge here, when you have this purely spatial process, is to accommodate the covariance across the space, but also among the components at each of the sites, right? And with Alan, we worked on an extension of the linear model of coordinalization that was originally proposed by Guller and Volz in 1992, where we allowed, we we obtained non-separable and non-stationary covariance matrices. How? We included this linear, so the Z here, so Y is a vector, it's a Q-dimensional vector. Z here is a Q-dimensional vector of independent Gaussian processes. And A is a matrix that is usually lower triangular. And so for each component of Y, we have a linear combination of these Zs. Okay, and what we did in comparison, and this was a paper that was co-authored by Alan, myself, Sudeep, that was published in Test with Discussion, we allowed this matrix A to change across space following two different proposals. One, that this, because if you look at AA transpose captures the covariance among the components of Y, okay? So you can think about the covariance as a function of a covariate times a matrix, a fixed matrix omega. This transformation here is varying with space. Another possibility, the one that we proposed in the paper, was this spatial Wishart process. So we borrowed the idea of how a Wishart distribution is constructed, if you will, such that these U's are independent Gaussian processes. And you have this lambda matrix, which will play the role of the scale matrix of the Wishart distribution. It's a bit challenging to, so the lambda matrix will be a hyperparameter in the prior for this matrix omega S. And omega S is changing across space because of these Gaussian processes here. So it's quite challenging to think about this prior specification of hand, because you have to define the correlation function of each of these Gaussian processes. You have to define this matrix lambda. So what we are proposing is a particular case of this model, where now, instead of making the U's to change across space here, we will allow the lambdas to change across space. But they will change across space. We will have a diagonal lambda matrix. Let's look at a two-dimensional problem to try and understand what is happening here. So basically, the A matrix, which will define this linear combination of these independent Gaussian processes, will be the product of this diagonal matrix by the matrix A, which we propose to be a Cholesky decomposition of the covariance, if you will, among the components, and then you have the two processes. The good thing about this parameterization is that each of these processes, because we are going to follow Palacios and Steele, each of these processes will follow a Gaussian process. And for each of the components, lambda 1 is involved only with the first component, and lambda 2 is involved only with the second. If we change the order, if we propose A times lambda, then lambda 1 would also be involved with the second component. We want to avoid that because lambda k is the component inducing the heavy tail of each of the processes. So, if you assume each of the lambdas following a priori a gamma prior with parameters vk over 2 and vk over 2, what you have for each of the components is a student T process. But as I said, we follow Palacios and Steele, and also Bueno and others 2017, and we model the log of lambda as this linear combination. So in Palacios and Steele, they didn't have this covariate information. They just had minus nu k over 2, and plus this arrow that is spatially correlated. We are inducing this component here to try and extract information from the data about covariate association in the scaling mixture parameter. So if you look at the properties of this log Gaussian process that goes in the denominator, because again, if you look at this equation here, basically what is happening with each of the components, just to remind ourselves, what is happening with each of the components is that lambda is entering the denominator, right? So, so if we don't have covariates, the mean of lambda is 1, and when nu k increases, the distribution of lambda becomes more right-skewed. So it induces, nu k is the parameter that induces the heavy tail. And we can look at the covariance, the cross-covariance, and the marginal variance of each of the components of this vector y, of this q-dimensional vector y. And we see, in terms of the variance, if we have covariant information in the log of lambda, the marginal variance, when we marginalize with respect to lambda, will also depend on covariance. And the conditional covariance between the vectors at any two locations will also be a function of this mixing component lambda. We can also look at the marginal spatial correlation and the cross correlation. If we look at the marginal correlations, it will be isotropic because we don't get the influence of covariance here. It doesn't change locally. But our goal is really to change locally the variance of the processes. And like in the Palacios and Steele paper, each of the components, if we look at the marginal distribution with respect to the lambda, each of the components have zero skewness, and the kurtosis depends on the parameter nu k. So nu k is really has a key role here of controlling the thickness of the tail. Well, we have to, as Bayesians, we assign prior distributions to the components. For the coefficients, for the fixed effects, we follow zero normal priors with some fixed variance. For the A matrix that is capturing the covariance among the components of Y across a space, we actually decompose it as a diagonal matrix with the standard deviation times A star, which is a Cholesky factor of the correlation at each location. And for A star, we assign a LKJ prior with some parameter alpha. For the scale parameters tau, which is the nugget effect, and sigma k that goes in this matrix A, we assign half Cauchy priors. For the range parameters, we think about them in terms of the observed distance that we have. And for nu k, this parameter that is controlling the thickness of the tail, we assign a truncated normal distribution with some associated variance fixed at u for some value nu k star. And we implement this in STAN, and it seems to work well, and we check convergence with using standard diagnostic tools. So we simulated some data. I know that this plot, I don't know how you see it here on the screen. It looks a bit psychedelic because in each panel here, we have the posterior summary of from 25 different samples. We wanted to see how able we were to recover the parameters that were used to generate the data. The dashed line in each panel is the true value of the associated parameter. And you'll see different lines for each of the samples because we are changing the prior for nu k because we want to see how sensitive the posterior distribution is to the specification of nu k. For most of the parameters, the posterior doesn't look that sensitive, but for nu, for the posterior distribution of nu, the greater the prior variance is, the greater the range of the credible interval. And if we go back to the UK data, here we have the observations of ozone on the left and PM10 on the right for June 23, 2020. And we see that there seems to be some spatial structure. For PM10, some of the locations have apparently atypical high values. And we fit three different versions of the model. We fit three different versions of the model. One that is the usual linear model of correlation as we proposed back in 2004. Then the GLG, because as the outcome vector is two-dimensional, I can think about the log lambda process in different ways for each of the processes. I can follow Palacios and Steele and just say that log of lambda k follows a Gaussian process centered at minus nu k over 2 with some variance and correlation, variance nu k and correlation structure. I can use covariant information. In this case, I think we use altitude, I don't remember right now. And, but I could also have different structures of the log of lambda for each of the components. This is what the fourth line refers to. In red, so we are using the energy score, the the variogram score and the log score and the interval score to compare the models. For all these criteria, the smaller the better, and in red you have the smaller values under each of the models. It seems that the GLG model, so the one that doesn't have covariate information in the log lambda process, is the best. And if we look at the posterior summary, I think it's interesting to compare the coefficients that we estimate from the Gaussian model and the coefficients that we estimate from the best proposed model, if you will, which is the GLG. What is interesting to see and to compare is the scale for the first process for ozone. The standard deviation is estimated at 10.46. When we look at the estimate under our proposed model, it reduces a lot. Of course, it's doing what it's supposed to do, because we have this fixed scale parameter, and then locally we are accommodating because we have this log of lambda 1 and log of lambda 2 for ozone and PM10 that is capturing what is happening with the scale of the distribution locally. So it's natural to see this reduction. And this reduction is being induced by the nulls, which are the ones inducing the fat tail. And we see that the posterior distribution is quite far from zero. We see some reduction in the standard deviation of the measurement errors, again, I think as expected, maybe suggesting that when we fit the Gaussian model, there is still some structure left in the residuals and that the model is accommodating. Again, another psychedelic plot, but here what we are looking at is, because if you recall, what we have is 1 over the square root of each of the lambdas multiplying that matrix A. So the greater this is, the more I'm inflating the variance, the smaller, the more I'm deflating the variance at each location. So I have all the locations here, and the dotted line represents 1, which is the Gaussian model. All of them are kind of touching 1, but what we can observe when we include covariates in the mean structure of log of lambda, the range of the credible interval reduces a little bit, but we see that at some sites the increase is quite high. In terms of point estimates, the point estimates are quite similar. Here are the point estimates of the log of lambda, actually of 1 over the square root of lambda at each location, just to see a spatial pattern. But if we look at the fitted values, what we can observe is that at some locations, the crosses here are the actual observed values. The pink line represents the summary, the 95% credible interval under the Gaussian model, and the others under the different parameterizations of our proposed approach. And what is happening is that the ranges, as we expected, the ranges of these credible intervals are adapting locally. But what happens, again, we have different processes, right? Because in the likelihood, we have a QN dimensional multivariate normal distribution. Then we have these n Gaussian processes for each of the scale components. What happens when n increases? Well, as probably most of you know, vacuum approximations have been quite used since the paper by Abhidata, Sudipto Banerjee, Andrew Feeling, and Alan Gelfand, where they extend the vacuum approximation to define the nearest neighbor Gaussian process. And the idea is very nice because you break this multivariate distribution into the product of conditional distributions, and you kind of truncate here on a subset. The point is that we have to approximate both this multivariate, in the example, a 2n dimensional multivariate normal distribution, and then these n 2n again normal distributions. So we follow, for the outcome component, we follow the proposal of the response NNGP that is described in this paper by Andrew Feeling and at JCGS in 2019. Basically, we can obtain all the conditional distributions because, again, conditional on the lambda, the mixing parameter, we have multivariate normal distributions. And the same can be done a similar approach, the NNGP approach, can be used for the latent processes, and we just have to compute these conditional means and variances, but we have to define the number of neighbors that we are considering to define this conditioning set, and they suggest that this number should be between 10 and 25. We tried different values, and we fixed them at 15, and also we have to define these neighboring sets. How do we choose these neighboring sets? And there is quite a bit of discussion in the literature, and we consider orderings based on maximum minimum distance and ordering of the x-coordinate. And as we decided to code this model in STAN, it was a decision we made when we started working with this. We are also taking advantage of vectorization and non-centering parameterization as proposed in this paper by Wang and Reinhard Führer in STAT in 2018, which kind of sped up the inference quite a bit. We simulated data from the model for considering 300 sites. And why are you considering 300 sites? Because it's the one number that STAN can handle with the exact model. So we compared using the two different NNGP approaches that we are considering. Basically, it's the neighboring set that is changing. And for all the parameters, it seems that we are recovering the parameters and the results are not different. So it doesn't make much difference changing the neighboring set. In terms of time, there is quite a bit of gain. To fit the exact model, it takes about 20 hours. When you use the NNGP, it takes about 2.7 or 2.47, depending on the neighborhood structure you use. We were planning to show you some data from pollution levels across Italy, but unfortunately, we didn't get the results ready for this talk, but we are working on environmental data analysis to considering more sites, where in this Italian example, we have about more than 500 sites. But what about a multivariate? What about extending this model to the spatiotemporal case? This would be an extension of the Series C paper that we did, but now the outcome vector, again, the outcome is a vector, it's a Q-dimensional vector. So basically, we follow our school at the Federal University of Rio de Janeiro of using dynamic linear models to account for the temporal structure that we have in our observations. So basically, we decompose the vector that we observe at time t, discrete time t, and continuous location s, as the sum of these three components. Epsilon t of s here is measurement error, and then ft of s times theta t is capturing this overall temporal trend, where the theta t's are allowed to evolve mostly with time, and wt is capturing the variability of this evolution across time. And then we have this local structure here, which follows the idea of the previous model, but now for each time t. So it's similar with the point now that now at each location we have the time series associated to each of the pollutants that we have. So again, this component, AT of S, ZT of S, is the linear model. The linear model, sometimes I can't see the pointer. It's the linear, here it is. It's the linear model of correlationalization. The Z's are Q-independent Gaussian processes. The ZTs, there is a T missing on the ZT1, ZT2, etc. And A follows, it's a Cholesky decomposition of the covariance. And lambda, again, is the diagonal matrix that is inducing the scale mixing component, allowing for a heavy-tailed distribution for the outcomes YT of S, okay? And ZT and the lambdas are independent processes. What about now? We have this lambda t for each of the components in the outcome. We have this Q-dimensional vector. For each of these components in the vector y, we need to define the mixing component. the lambda T of S. And we follow our Series C paper that was published last year, that we say that, and again, this follows the idea in Fonseca and Steele, but now with discrete time, and we include covariate information in the modeling of each of these processes. We decompose lambda KT of S as the product of a purely spatial process and a purely temporal process. So they are separable in this level of the lambda of the scale mixing component. And it will follow similar properties of those that I described when I was proposing the purely spatial, heavy-tailed multivariate spatial model. So again, the expected value of lambda 1, K of S, will depend on covariates. If we don't have covariates, this expected value is 1. And as nu 1K tends to 0, marginally lambda 1 is expected to be around the mean. And as nu 1K increases, the distribution becomes more right-skewed in the spatial direction. What about for the temporal structure? For the temporal structure, we put another layer of a dynamic linear model. So it follows similar ideas. We include covariates that vary across time, and we are allowing this component to also change as a function of covariates, such that the mixing component of each element of YT of S will change with space and time, and we are able to capture local structures of these pollutants that we are modeling. And again, we can compute the marginal variance, which will change across the space. And the correlation and the kurtosis now is a function of two nulls, because we have the one associated with the spatial component and the other one associated with the temporal component. So nu1 and nu2 for each of the components in the outcome vector will play the role of making the tail of the distribution thicker, of the marginal distributions. So in terms of prior specification, we are using, I think I haven't mentioned, but we are using for correlation functions, we are using the Martin with a smoothness parameter fixed at 3.5, and the range parameters of these Martins, the prior distribution follow gamma priors with parameters A and B, such that we consider the maximum and minimum observed distance in the data. Again, the correlation matrix is described as this product, and we have A star here as the lower triangular. It's the Cholesky decomposition of this correlation matrix. And we now have to assign prior distributions for each of the components. We have these nulls, and we use half-normal distributions with the variance fixed at some reasonable value. And the W's of the, I don't know if you remember at this point, but the W's, we have the W's in the evolution of the state vector that goes in the second, the temporal mixing component, but we also have W's in here, and following the dynamic linear model literature, we use the idea of discount factors to estimate these W's. Again, the posterior distribution doesn't have a closed form, and we implement this model in STAN again. The idea of implementing it in STAN is that hopefully it will be useful and accessible, and also to take advantage of the efficiency that STAN provides. As I said, the estimation of the evolution process use discount factor strategies. It's really key to marginalize the likelihood and the distribution of the log of lambda 2kt with respect to the state vector. This speeds up the computation quite a bit, and then we can recover them once we have a sample from the posterior distribution of the other parameters using composition sampling. And as I said, we approximate the posterior using STAN. I didn't mention anything about spatial interpolation when I was discussing the purely spatial process, but everything follows from the fact that given lambda, given the mixing component, everything is normal. So, and log of lambda itself follows a normal distribution. So we can use, again, properties of the partition of the normal distribution and approximate or obtain samples from the posterior predictive distribution when we want to do spatial interpolation within the observed temporal window, or when we want to do temporal prediction at observed sites, or when we want to do spatial temporal prediction. So this all can be done once we have a sample from the parameter vector associated with the proposed model. Again, we simulated different artificial data. Here I'm showing one example that we are trying to mimic the UK data, where we generated 25 replicates from the full model. So it's the model that allows for covariant information in the temporal mixing component, covariant information in the spatial component. And it seems that we are recovering the parameters. Again, each of the panels are showing the 25 posterior summaries for each of the parameters. The dotted line, dashed line in each of the panels represents the true value used to generate the data. And it seems that the 95% of most of the intervals cover the true values. But we also wanted to check if the model comparison criteria that we were planning to use would do a good job. So for one of the data sets, we removed we kind of did a cross validation such that we considered 5 different partitions of the data set, such that we fitted the model for 34 observations out of 37. So we removed 3 sites, and we removed also 16 points at the end of the time series to predict for those. And we fitted particular cases of the model. The Gaussian model is a particular case when we fix the both mixing components at 1. The GLG model, as proposed by Palacios and Steele, is the one that the spatial component lambda 1 follows the log follows this Gaussian process, and then the temporal one is fixed at 1. So on and so forth. So we have these different particular cases, and we know we generate the data from the full model. So we fitted all this. We fitted different models, and apparently the different criteria we are using, as I said before, energy score, variogram score, different values, and the log predictive score and the interval score seem to indicate that the full model is the best among the fitted ones. But what about the UK data that I showed you on the beginning? So we have 37 sites, and we have daily measurements of ozone and PM10 from May 15 to August 31. And here's one time series as an example. And the main structure of the models that we fit, they are all the same. They have a time varying intercept. They have longitude, latitude, altitude, daily mean temperature, and wind speed. And associated to each of the coefficients, they are allowed to evolve smoothly with time following a dynamic linear model structure. Then we have the cross-validation. Like we did in the artificial data analysis, we left out sites from the inference procedure to see, because we wanted to see how the models were performing. So basically this table, what this table is showing are the different criteria based on the fitted values, based on the spatial interpolation within the observed temporal window, and based on temporal prediction at the observed sites. And it seems that the model that considers covariant information in the lambda that varies with time, and purely dynamic structure for PM10 seems to be the model that performs better among the fitted ones. So the results I'm going to show are based on this model. Notice that we are considering a different structure for ozone and for PM10 in the log lambda. The scale mixing components, recall that they are the lambda for a given outcome is given by the product of a scale, a spatially scale mixing and a temporal one. So we are using different ones for the different components. Again, we have the posterior summary, like we did in the purely spatial example. We have the posterior summary of the parameters. We see this reduction of the standard deviation as we would expect, because again, we have a component in the model that is capturing this scale locally. And the nulls seem to be far from 0, with median at 1 1.39 for ozone and 1.68 for PM10. Here are the posterior summaries of the coefficients, of the time-varying coefficients that go in the mean for ozone. On the top, the 2 rows are associated with ozone. On the bottom, the ones associated with PM10. We see that for temperature, there is a counterintuitive result here, at least for me, that temperatures is negative. The association is negative with ozone. And wind speed, I think, as expected, has a positive association. And when we see with PM10, the results seem to make sense. A negative association with altitude and PM10 seem to have a negative association, whereas wind speed doesn't seem to be important. But we also have covariates in the log of the lambdas, right? So here are the covariates that are entering. Temperature and wind speed are entering in the temporal component of the lambda that is mixing for ozone. And it's interesting because we see a negative association with the log of lambda. So as the temperature as the temperature increases, what we see is a decay on the precision. If there is a decay on the precision, we have an inflation of the variance. For PM10, we have just a time-varying intercept in the mixing component. And these are the posterior summaries that we have for each of the components. For ozone here and PM10, we have both spatially and temporal structures in the mixing components. So we can identify the sites that required greater values of the mixing component to try and understand what is happening. I like this plot because what it's showing, each of the panels are the sites that we left out from the inference procedure. And if you fix at one panel, the gray line represents the posterior, the standard deviation of the posterior predictive distribution. So if you, under the normal model, so normal for both PM10 and ozone. And here, the solid black line is the standard deviation estimated from our proposed model. And we clearly see that the Gaussian model is unable to accommodate locally, whereas our proposal is accommodating, is increasing when it needs to be increased, and it's decreasing when you don't need a big variance. And we can see this with the posterior summary of the predictive values. I'm almost reaching my time. I have other 2 slides. I think. And here I have the summary of the predictive posterior distribution. The solid lines are showing the limits of the 95% posterior credible interval under the Gaussian model, whereas the shaded area is showing the posterior summary under our proposed approach. And as we can see clear for PM10, we are really adapting locally. The range of the credible interval seems to decrease, and the solid circles are the actual observed values that were not used for inference, and we seem to capture them reasonably well. So to conclude, we propose a particular class of purely spatial and spatiotemporal linear models of coregionalization that allow for marginal heavy tails of the components of the outcome. The proposal, we see it as an alternative to the spatial Wishart process that we originally proposed in our test paper in 2004. It's a Gaussian log Gaussian mixture model. It has close connections with Palacio and Steele in 2006, and also our extension in 2023. The marginal tails are controlled here. We believe that it's easier to understand how the tails of the distributions are controlled, and it's through this parameter nuK, and we believe that care must be taken when assigning the prior distribution for this parameter. We are investigating the scalability of the proposed approach for a reasonably big N, and we are currently developing approaches for the multivariate spatial temporal model. We perform the inference using Hamiltonian Monte Carlo through STAN, and we are also implementing the model in Nimble to compare how the 2 softwares behave and how different the time spent to run the codes take. The local structure in the variance account for different regimes of variability across space and time for the different outcome processes, and care must be taken, as I said, when thinking of structures for the mixing components. In the ozone PM10 data, UK data, we saw that for the ozone we have a different structure for the mixing component than for PM10. So we have to be kind of creative and think about different structures. All these models, they are isotropic, but we could consider covariate information in the covariance like what Marco and I did in our Valencia paper in 2011, where we were modeling fish abundance across the shorelines of a lake in Quebec, and we used geodetic depth as the covariate that entered in the covariance structure. So again, I would like to finish not again, because I haven't mentioned this yet, but I would like to finish by thanking Luigi Politi, Pasquale Valentini, and Carlo Zaccardi. I have been here in Italy for the last almost 6 months, and I visited them at UDA in Pescara, and I had a wonderful time discussing quite interesting environmental problems. So thank you very much for your hospitality and the great work we did. And again, I want to thank the scientific committee for inviting me. As I said, it's a great honor for me to be here today, and the organizing committee to put together this amazing meeting. I know how much work you have done, I really know. And I thank NSUC and FRQNT in Canada for the financial support, and Calcul Quebec for the servers to be able to run all these models. Grazie mille, muito obrigada in good Portuguese.
Hi. First, I want to say that it's a pleasure to see you talking about this. Alex is like a sister to me. We've known each other for like 3.5 decades. And she's the sister, you know, that I never had, and I'm the brother that she never had. I have 2 brothers, she has 2 sisters. But I have a real question, but I want to make another observation. You're just making the life of the other 3 keynote speakers really hard because you put the bar up there. I'm impressed by how similar the current tendency of modeling multivariate time series or spatial temporal time series using the scholastic decomposition. You see that a lot in macroeconomics, macroeconometrics, time series for causation. You can look at the paper that I wrote with Rob McCulloch. We propose a scholastic decomposition of 100 stocks, and we model everything time varying. But if you look at Mike West's work, recent Mike West's work on causal inference through dynamic models, he does something similar to that. And my question is, well, it's the same question people always ask me when I talk about scholastic decomposition. If you flip the order of these 2 time series or the 2 variables, how sensitive your results are, and how that scale, if you, in your case you have 2, but if you had like a 20 or 30 pollutants or other variables that you want to model jointly, that would create like a number of permutations that would be hard to know which one to use.
Can you hear me? Yes, I think so. When we initially proposed the linear model of co-regionalization, we had a full matrix A. We decided to use the scholastic decomposition because you can't identify, right? Because AA transpose will give you the covariance among the components of the vector. We investigated the order. I don't think there will be an effect. But very recently, Dave Stephens at McGill University and I, we are co-supervising a student, Renaud Ali, that he's proposing a model that we have a full matrix A, and he uses interweaving to try and estimate which A's should be included, such that, because the nice idea about this is that you can also estimate which components of the vector have zero correlated. So it's something that we have been thinking about.
Yes, so thanks for the talk. Again, so I'm working with David Bowling as well, so on this SPD approach and all that, and non-Gaussian latent field. Cabral has done that last year during his PhD. And one line that we have been following is that instead of directly thinking about a non-Gaussian latent model, you think first about model expansion. So you start with a Gaussian model, you feed that model, and you try to localize points where you think that depart from Gaussianity. And then you try to correct them starting from this Gaussian model. How do you think we could embed your framework in these ideas?
I think it's something that we could think about. Maybe instead of making all the lambdas changing across the space and time, maybe we could divide the region and have lambdas that are kind of localized, but bigger areas than local. I think you are presenting a poster here, and you mentioned that the other day.
Yes.
I remember well.
At 5.
I would like to see the poster, so let me know when you are presenting your
Today.
poster. Okay, great.
Thank you.
I will come and see you.
Hello. Thank you, Alex, for the wonderful talk. You answered more or less my question at the end in your conclusion remarks. When you look at new, and you say, oh, you need to be very careful with the priors. Flavio and I has been thinking about this problem in the spatial context, and we are convinced that that new is non-identifiable by the likelihood, because you have one replicate usually. On the spatial temporal, maybe you can go through the dynamic and it probably work better. So I would like to see your take on, because we're basically saying you need to give informative priors and defend them, of course, because that's what will guide your new.
I don't feel very uncomfortable. I don't feel uncomfortable about assigning informative priors to new, because if you do the exercise of generating data from the prior predictive process, you will see that new, as it grows large, it will provide realizations that are quite heavy-tailed. So I think we can perform exercises like Jake Adani once told me in one of the Valencia meetings, that just generate data from your model to see how it behaves depending on the price specification that you have. And you will see that if nu grows too large, the details will be too heavy and unrealistic for the processes that you are modeling. So I think there is a way around that. And about the unidentifiability, maybe nu suffers from the same problem that the degrees of freedom of the T has, and that Thais, Hélio Migon, and Marco Ferreira has a nice paper about this in Biometrica in 2008, if I'm not mistaken. Thank you very much. Thank you.